substrate B. Oops. So how can we describe this? First, we know our substrate has an initial rate. Measurement can be performed to determine kinetics. So the first point we have to remember is that we have an initial rate measurement. And if we analyze this, we come to the standard Michaelis-Menten plot, which is initial rate times concentration of B. And then we do have here the normal expected hyperbolic course of the Michaelis-Menten rate with Ca equals constant. So that was what we were doing the whole time. And now we have different concentrations of B. And those are concentrations, just in our example, we're going to use in a moment. So we have one out of the range of first order, one of mixed order, and one out of zero order. And those we are naming CB1, CB2, and CB3. So CB3 is the highest concentration we have to observe. Now, then we normally determine enzyme stability studies. Let's see a new, too thick too bold my pen, sorry. So more room on the right side. Rate measurement. So that's the kinetics we just discussed. And then the second point is that we can do enzyme stability studies. So how do we analyze enzyme stability? Well, in the end, how we do this, we have a Eppendorf cap, so a small reaction vessel. And in this reaction vessel, we add our enzyme, plus we add a specific concentration of B. And this we incubate at a set buffer concentration, at a set pH value, and at a set temperature with time. And now, let's say every 10 minutes or every hour, we withdraw a sample. Meaning here in our incubation system, in the end, no reaction is taking place. We do have our enzyme. We do have only one substrate, Ca is missing, under defined buffer pH and temperature conditions. So no reactions going on. We're incubating with the reagent B. Then we're taking a sample. And additionally, at this point, we're adding concentration A to the sample. And maybe if we want to adjust the concentration of B, maybe still some concentration of B. With this, we have now some concentration for the initial rate measurement. And now we can generate out of this what we're measuring here, initial rate as function of time, namely those time points here that we withdraw the sample. So the sample time will be the time point that we have here on the initial rate axis. Okay, that would be the procedure. So what do we see in our analytics at the end of the day then? Then we generate out of this data we just measured a plot where we now plot not initial rate, but rate as function of time. And this time is a time, oops, sorry. And this time here is the time we have here in the plot and the time where we've withdrawn the sample. Now, let's start with the ideal scenario. So we do not observe any enzyme deactivation. So no enzyme deactivation, ideal situation. If this is true, then we would result in a constant line parallel to the x-axis for the different CB3, CB2, and CB1. What is important to know here is that we do have different starting points here, resulting in the different concentrations that we had set here. And therefore, it has to be different starting points. Ideal situation. In a realistic case now, we have, or in our special case we're studying right now, we do have enzyme deactivation by the second substrate B. So in other terms, we would not observe these orange curves you see here, but we would observe something like this. So deactivation with time. And these will for sure start at different levels because we have different substrate concentrations. So if we're taking a closer look, we see that we have, depending on the different starting concentration, and if we determine here the initial rate of enzyme deactivation, different rates resulting. And that is now a challenge. How can we describe this mathematically in overall simulation model? Well, the trick is that we use normalization. So how does this function? In the end, we generate once again a plot V divided as function of time. So that's the right plot on top, right? But we do not plot V, but we plot V divided by V0. And this V0 we're talking about here is the V0 we have always here as a starting point for the different concentrations of B. So if we run this normalization, in the end, what we're doing is that we set all these three concentrations to the same point up here. And in consequence, under ideal conditions, for all three concentrations, we generate a plot where we have one line in parallel to the x-axis. Now, in the non-ideal situation, what we're discussing here, that we see a deactivation by the starting material B, we would rather see then the deactivation. And since V has the highest concentration here and the highest rate, we will also see the highest deactivation rate in this normalized plot. And in consequence, we will see a fast deactivation in the case of CB3, CB2, and CB1. So this is ideal, and in case of the deactivation, and that's not important, this is CB1, CB2, and CB3. Now we have here a degradation, so that's enzyme, same approach that we used in before in the case of enzyme thermic enzyme deactivation. Let me quickly change back to the transparency before returning here. So this was what we just had, thermal deactivation, and we had described the thermal enzyme deactivation with a deactivation rate constant depending on the active enzyme. And by integration, we yielded this term that can then be used to formulate that the concentration of E, change of concentration of the active enzyme by time equals minus concentration of E times the deactivation constant. And the same we will do now. We want to formulate a term only that the deactivation is not thermally motivated, but by a second substrate. Okay, going back to our whiteboard. No, I lost my mouse. Sorry, sometimes this happens in the presentation mode. Okay, now you see my whiteboard again. So that's the scenario. So therefore, we need to determine now a K deactivation 1, a K deactivation 2, and a K deactivation for concentration 3. Now, with this information, or this knowledge, we now need to formulate a kinetic description of the rate of deactivation. And to do so, what we're doing now in the following step, is that we're taking these values of the deactivation constant and we're going to express them as function of the concentrations of B, the concentration of our substrate that initiates the deactivation. And that is in the end, next step that we are now doing. The topic is still enzyme deactivation by B. So now we can generate a plot out of this measured data and normalized data, where we plot the different deactivation rates as function of the concentration of B. And if we're doing this, we will find out that we once again get a hyperbolic correlation. And in this hyperbolic correlation, just mathematically a hyperbolic curve, we can always describe by 2 parameters, what in Michael's Menten we name Vmax, so that's A, and then the half maximal rate, the activation rate here, is then parameter B. So same approach as in the Michael-Menten curve, and therefore we can make use of the standard hyperbolic form, that mathematical form, that we can then say, okay, the deactivation rate not for a specific constant, but generally for B equals A times concentration of B divided by B plus a concentration of CB. And this A, what we see here, is this A, and this B is this B. So now we have generated a mathematical description of a deactivation constant that is depending on the concentration of the second substrate B. And in consequence, we can also formulate, once again, a rate law that we have that the change of concentration in the enzyme by time equals minus concentration of E times the deactivation constant for B in our case. And for sure, if the deactivation is not in B but is in A, we can formulate the same thing, that we say the concentration of E is changing by time minus concentration of E times the deactivation constant in A. So now we can integrate this in our overall simulation model. And we do have a full description. So we consider thermal deactivation of the enzyme. We consider deactivation of one of the reactants. And if it would be deactivation by the product, it would be the same. We would have the same approach to describe it and integrate it. Yeah, so we're close to describing a full realistic model, but one thing we're still missing. One complication also often takes place, and that's the last thing that we're discussing here in the standard simulation approach of enzymatic biotransformations. What could that be? Well, it will be if our product is not stable. So we are discussing here the unlucky cases that you can encounter in industry. And the unlucky cases that you have a limited product stability in the given reaction system, meaning that you need to hurry up to do downstream processing to isolate your product or even do in situ product removal. A typical case that we already discussed is the degradation of NADPH, the cofactor, the phosphorylated cofactor. If you remember one of the first lectures on oxidorotases and their hydrogenases in the biocatalysis enzyme technology. Yeah, so topic that we're now discussing is chemical product degradation. And example, we might have NADP+ that by means of the hydrogenase, you need to remember the other lecture, with molecular hydrogen, we generate NADPH, but now you're unlucky, and that is degrading to side product Z that is not wanted. Yeah, and in consequence, we need to describe this. And this is not only true for NADPH. You can use this now for any product that you would like to describe. And just to use the most complicated case or the most complicated formulation we can think of, so far we did all the simple stuff. Let's assume we want to describe this in the CSTR. In the CSTR, we most often observe this in terms of deactivation of a product, because remember, CSTR, we're operating under outflow conditions. So we always do have the highest possible product concentration. What is our aim? But then, at the same time point, if the product concentration is at its highest concentration, we also have the highest concentration for the follow-up reaction in terms of this degradation, what we do not want. Okay, so how do we describe this? Well, we need to describe the change of concentration in T by time. And that equals, now comes the residence time term for the CCR. So we have the concentration of the product minus the concentration of the product at time point 0 divided by the residence time plus now the kinetics for generation of the product. So that's the reaction rate, kinetical term there, double substrate, kinetics, Michaelis-Menten, or whatever you would like to choose, times the concentration of the enzyme, and the term needs to be positive because it's product generation. And now, not discussing it in any more detail because we discussed degradation, deactivation in detail, but then it's minus the concentration of P times the deactivation term. In the same manner as we described it beforehand for B, for example. Yeah, and with this, we can clearly describe chemical product degradation. One question I have, and I forgot to do a Mentimeter question for this, but maybe you can open up your microphone and just talk in here. And the question is, why do we subtract from our present concentration of the product, concentration of the product at time point 0? Why should we have product at time point 0? Does anyone has an idea? You can alternatively also write into the chat or open up your microphone as you like to. Nah, you're hesitating. No idea. Recycle stream. Yep, that could be one point. But in the recycle stream, to be honest, so what you're thinking of is we have, for example, the circulation loop reactor that I introduced to you, and we have here the recycle pump. And we have the flux 2, and here we have the other pump generating the flux 1. And your idea is because of the recycle stream, but at the end of the day, this is the overall reactor volume, the reaction volume, where the volume is a term in the residence time formulation, where we have tau equals volume divided by flux. And the flux that we have in here is this flux generated, so we could name it also flux 1. And since we are operating under outflow conditions in this cycle loop, the outflow conditions is true, and therefore, yeah, it should be equal the concentration, and we should not have any product if we start up left just because of the recycle stream. It might be that we can observe some, like everywhere, but it's not the real reason. You have other ideas? And F2 side condition needs to be at least 20 times the flux of 1. Other ideas? We're talking now about realistic production systems in industry. Well, the point is maybe the workers from the last shift who cleaned up the reactor for a restart did not clean it totally finally. And so often in these connection flanges that there are, where there are, for example, tubings are welded to a big reactor, often if you have a solid product, for example, there are some dead volumes where something is trapped that will be resolubilized in the reactor system or something like this. Yeah. Okay. Yeah, with this, we're almost at the end of simulation. So I've demonstrated to you how you can run a simulation for standard biotransformation in continuously as well as batch operated reactors, and how you can consider realistic terms. This was just one reaction with multiple starting tubes. What we still need to discuss shortly or briefly is if we have a reaction sequence that we would like to model. And to model the reaction sequence, there the example that we are using is cofactor regeneration system that I would like to discuss with you at the last example for simulation of biotransformations. So the topic we're discussing now will be complex reaction systems, and these handwritten transparencies you will find already in the PDF that I've uploaded from last semester. Maybe I draw something a little bit different, but it's the same content. So complex reaction systems with Michaelis-Menten kinetics, just as the most simple one. Okay, what does this mean? This means that we starting up our standard system will be with a ketone, and this ketone we just name also ketone or CAT as abbreviation for the following. then this we're going to reduce with an alcohol dehydrogenase. And out of this, we are generating an alcohol. For sure, it will be chiral, otherwise we wouldn't invest the time. Sorry, just joking. This we abbreviate with alcohol for index. It's English, so it will be C. Yeah, and then we need cofactor. So we have the cofactor recyclization term. And for the reduction, we need the reduced cofactor NADH, generating the oxidized cofactor NAD+, which now at the same time point will be the cofactors being used in the cofactor regeneration. And we are discussing two cases because we discussed there are two principal cases, that's the enzyme coupled and the substrate coupled cofactor regeneration. We're starting up here with the enzyme coupled, so making use of a second enzyme. So that will be formate dehydrogenase. And so we're utilizing a second starting material, formate, that we are abbreviating with form, and we're generating as co-product carbon dioxide. The big advantage is that if you remember the Biocatalysis enzyme engineering lecture, that the KEQ for the FDH is approximately 15,000, meaning that the equilibrium for the FDH is totally on the side of the carbon dioxide, not because the carbon dioxide is degassing, but because the equilibrium constant is so high. And because of this, this reaction is formally irreversible. So therefore, we can make the assumption irreversible also being true then for our target reaction. This means we do not need to consider backward reaction. So we're just saying irreversible because this is irreversible. We're linked by the cofactor regeneration, and consequently also our major reaction will be irreversible. So if we now express this and transform it to our mass balances and differential equations, then we can formulate for the system in the same manner as we practiced it beforehand this morning, that we say, okay, the concentration change of the ketone that is being consumed by time equals the and now we are describing this. I should add, sorry, for batch reaction. The same approach is true for the CCR or PFR, then you just need to add the residence time term, what we discussed last time. So therefore, we say, okay, we have a specific concentration of the alcohol dehydrogenase we're adding to the system, and this is multiplied by the negative rate of ADH in the reduction mode. This is now important in the reduction mode because this will look different if we describe it in a different manner, as you will see in a moment. Then we do have our first substrate we just described, but the second substrate is a cofactor. And now we have to consider one specific if we're describing the cofactor concentration change with time. Why is it important to consider what's going on here? Well, our starting material, the ketone, is just being consumed by the alcohol dehydrogenase. But this is not true for the nicotinamide cofactor. This will be consumed by the alcohol dehydrogenase, but at the same time, it will be formed by the formate dehydrogenase. Therefore, this looks different now. So if we formulate a change of the concentration, and let's say we now take the reduced cofactor NADH divided by dt by the time, then we can once again say, okay, this cofactor is now dependent on the concentration of the ADH times, in the end, equal term here, because the rate of consumption determines the rate of consumption of the cofactor. So therefore we can once again write minus reaction rate ADH reductive. But that is now, as we discussed before, just half of the story, because this lower reaction generating ADH is missing, and therefore we have to consider this and also add up. So therefore we say this multiplied term needs to be added by a term where we say the concentration of the FDH we set in times the rate of the FDH for the FDH reaction in the oxidation reaction. And this now, I'm not going through this in more detail. We can now continue to formulate, following this approach, for any of the reaction components. So we can describe this for the NAD plus. There, then the term would be positive. Then here the term for the FDH would be negative in this range. So this is how we can describe it. Any questions up to this point? Okay, I don't see any. So now here you're lucky with the FDH, because with the FDH we have the big advantage, we have a KEQ of 15,000. Therefore we're saying this thing here we're discussing is irreversible. But now if we would describe the same system either in a substrate coupled approach or in an approach like with the glucose oxidase, for example, so different enzyme that is doing the recirculation, the story will look different, because we would have an equilibrium we need to consider, and the last point for this complex reaction system we're discussing. So complex reaction system with kinetics. So I'm just doing it a little bit faster here. We have the ketone, we have the alcohol, we're producing, we have a forward reaction, but we also have a backward reaction. So we are now in equilibrium position, meaning that also if you have the cofactor NADH and NAD plus reaction product, this once again will be forward reaction, but it also will be backward reaction. And remember, I did it wrong here. In the equilibrium, we always use these half arrows and not the full arrow. And this is also true then for the recirculation. And this is true for the cofactor regeneration. We would have this arrow. And then we would have as a target enzyme doing our target reaction, the ADH. And let's say that we're using for the oxidation, we might use glucose dehydrogenase, which we discussed it also in the other lecture. And this is has not an equilibrium conversion of 15,000 equilibrium constant. So it will be lower, and it might be that we need to consider the reaction equilibrium or like in a substrate coupled system. And so we would have glucose, lactone. And now the formulation would be the same approach like what we had before for the ketone. So we consider the concentration change of the ketone by time, which equals the concentration of ADH. And that is just the one-time concentration that's in the whole batch. Therefore, it's just one concentration, but two rates we now need to consider. Namely, now we need to consider the rate of consumption of the product by ADH in the reduction mode plus the rate of the ADH in the oxidation mode. And if you're now considering the cofactor, it's the same approach, therefore the term becomes a bit bigger. So once again, we would now want to describe the concentration change of NADH by time. Then it will be the same term we just had. So concentration of ADH for the substrate, second substrate, its rate of ADH minus for the reduction, plus the rate of the ADH in the oxidation mode, what is the reverse reaction. And now the NADH is being formed in the starting up from glucose with glucose dehydrogenase. So it will be plus the concentration of the glucose dehydrogenase times the rate. Now it's being generated, rate of glucose dehydrogenase in the reduction mode minus, that's the consumption, reverse reaction of glucose dehydrogenase in the oxidation. Yeah, and with this, we have described the whole system, and we can now continue this for all reaction components. Yeah, I hope I could make clear to you how the system functions and how you set up simple simulation models and for describing kinetical reaction systems. Now, the last thing we're doing before we're starting up with immobilization today is we want to discuss a very special case, which is a challenge to understand, I know, but that on the other hand is now making use of all that we discussed so far, and it requires some thinking effort. I'm switching back to the transparencies. And that is kinetic resolutions. So we discussed so far two substrate reactions leading to one or two substrates. We discussed thermic deactivation. We discussed the activation by a second reagent, by a second substrate. We discussed product degradation. We discussed reaction systems where we have multi-step reactions and how we combine them in the formulation. The last thing we have to discuss is now kinetic resolutions. You remember Biocatalysis enzyme technology lecture? We have kinetic resolutions in different types of reactions that we can apply. This can be kinetic resolution with alcohol dehydrogenase by oxidizing racemic alcohol. This could be the use of the transaminase. This could be the use of the kinetic resolution by means of a hydrolase, and there are multitude other opportunities that we even did not discuss. Now, coming back here, that's our standard example from the hydrolase reaction with lipase. So we have a chiral hydroxy ester, which has an enantiomeric excess for the substrate. With water in the forward reaction, we are catalyzing the hydrolysis, catalyzed by lipase, forming a product which once again has enantiomeric excess. Okay. This system we discussed in detail, and remember we generated these plots where we plot enantiomeric excess as function of the conversion, and we said if in ideal manner we have, forget the yield curve here, we're just focusing now on the EE as function of the conversion. We said in ideal manner we have in kinetic resolution 50% conversion, 100% EE. In the case that the reaction is not ideal, we said we have this big E, this enantiomer activity term, and if we have a value of 35, that's the point we're considering to apply as an industry, and there we need around 60% conversion to have 100% EE. So that was discussed all over. I hope you remember this and have understood this. If not, talk to your classmates, or in the next lecture I will finalize the invitation. We will not manage everything today, and then the second half of next lecture and the next lecture we will do practice and case studies where you can still ask questions what you have not understood, and I'm happily would like to explain it. Now, assuming you have understood all this until this point, my question to you is, if you need to run it continuously, what reactor would you choose? Or would you just do the batch? Or if it's not a batch and you run continuously, what would be the reactor you're choosing? Kinetic resolution, as we discussed before. And prior giving you an answer here, I want you to think about it. And therefore, we're switching now over to millimeter. And the code for today is 207037116. Menti.com, and I'm waiting for you to join in. I think we have how many people in the lecture? 38 people in the lecture. So, yeah, waiting until the majority has joined in. Okay, we have 24. Okay, number seems to be stable. Then we're starting over. You have 1.5 minutes to think about what from your point of view would be the right answer. So kinetic resolution, what reactor to choose? Batch, plug flow, or CCR? There are more than one answer is right, but one for sure is wrong. And we will discuss this afterwards. Take your time. Okay. Yeah, so batch would have been the right reactor. A plug flow reactor would be right. If you use a CSTR, you have lost, and really lost, because you would have not generated any money for your company, but destroyed it. Okay, why is this the case? No, before we discuss this, we're taking a look at the leaderboard. Okay, so fastest one are Ashley and Vedat, so they're, I think, equal. Then Simba, Vroom, Beyonce, Brasalise, Beyonce the second, HG Love Side, and so on. Okay, switching back to our lecture. What's going on here? Well, before we dive into this, let's remember what's going on. We said the plug flow reactor is a continuous version of the batch reaction. Therefore, both were right, because if the batch is right, the plug flow reactor needs to be right. The CSTR, and this is now the very important point you need to burn into your brain, operates under outflow conditions. Meaning, at every location within this reactor volume, we have the same concentration as in the outlet. Okay. This means also, if something enters this reactor at the inlet, high starting material concentration, it will be directly transformed to small part that enters here, low concentration, first order kinetics, therefore high enzyme consumption, to the maximum product concentration. In the plug flow reactor, sorry, it's a case that the product is being formed as function of the length of the reactor, and the starting material is decreasing as function of the length of the reactor. Meaning, if our starting material entering here, it will enter at maximum starting material concentration and stay this way for a long time and slowly degrading. Now replace the word starting material with racemate. If you're running a kinetic resolution, then we're entering with a racemate to these two reactors. The aim of the reactor, and let's say we're sticking now with the 35 curve, 30 in activity 35, this blue curve here, meaning we need 60% conversion to reach 100% EE. If that is our system, and just thinking back principally about these plots before we're looking at any XY plots, we're entering in the plug flow reactor here with a racemate. And this racemate, in this racemate, now the second enantiomer, making out of two enantiomer complementary enantiomers, the second enantiomer is degrading by time very fast, and the second one is very slowly degraded. In the CSTR, it's different. We're also entering with the racemate, but here we are already at the end point in the reactor at the outflow condition, what we just have here. So the kinetic resolution performed finally is in the plug flow reactor just at this output flow point here of this column. In the CSTR, it's all over the reactor. So we have, in principle, already reached this endpoint, namely this one up here, but we cannot reach it, never ever in the CSTR, because we're constantly to this endpoint adding racemate. And that is why the CSTR is not applicable in a kinetic resolution if the kinetic resolution is not ideal. If we now want to see this in realistic manners and we plot for the system EE as function of conversion, you see a simulation for a given reaction system, but the rate is 35, the initial activity. You can see the dashed line is that of a batch or equals the plug flow reactor, where we need approximately 60% conversion to yield 100% EE. Because of the spec mixing under outflow conditions, the red line, the CSTR, you see we even never reach 100% DE, so we're stuck somewhere with 95 in that range. So therefore, you have to, fundamental principle, if you want to run a kinetic resolution, chemically or biocatalytically, your first choice will always be a batch reactor or a plug flow reactor. You will stay away from a CSTR. And this can, oh, sorry, this is strong. Translate. So here you see the residual concentration substrate divided by the substrate at time point 0 for the R enantiomer, and down here for the S enantiomer. And this is now plotted for to compare it for the batch reactor by the product of the enzyme concentration times the reaction time. That's because to normalize these two reactors to compare them. And in the CSTR, we have the product of enzyme concentration times not now the reaction time, but the residence time. And now if we plot those, the CSTR is the closed line and the dashed line is the batch reactor. Let's stick with the batch reactor. If you have a ratio, enantiomer activity of 35 means, here in our specific case, the S enantiomer is reacting 35 times faster than the R enantiomer. And therefore, in the batch reactor, the S is decreasing with function of time. The R is also reacting, is also decreasing in the batch reactor with time. Now we're looking just at this dashed line, and we determine where we have, and for comparison point, we have here selected a conversion of 55% conversion point. Then if we have almost none of the S left, and our target is in almost very slow converted R, we have a residual amount of concentration of 90% of the R substrate, whereby the S has almost reacted away. In case of the CSTR, we have the big disadvantage that at the point of high conversion, we always re-add racemate, the wrong enantiomer, to our final conversion point. And in consequence, for the S, the fast reacting enantiomer in the batch almost consumed, we will never reach this point because at the inlet, we are always adding here the racemate to the high conversion point and the high EE we formerly would have had. And therefore, if we look at the conversion point for 55%, we have consumed more of the R enantiomer, but we have more left over of the S because of the remixing in the CSTR and readdition of the racemate. I hope this is understandable for you. I know it's a little bit challenging. And why don't you think about this after lecture, maybe talk with some of your colleagues, and we will also have one example later on at the end of the semester again. Now, we could do this more generally, and so just by traffic lights, we were thinking about kinetic resolutions. So the best thing would be batch reactor, plug flow reactor, and a repetitive batch where the enzyme is filtered off and reused, same performance as batch. So the best choice for you for kinetic resolution would be batch, repetitive batch, and plug flow reactor. The CSTR is a no-go, red traffic light, because we will never reach this point. So here the small black line, that's the ideal situation, and the blue one is the one that's shown here. The fat batch, so if we run a batch where we constantly add starting material, we are in the same bad situation as with the CSTR. It's not that bad, but in the end, we need higher conversion points, so you won't do this And then we could say, okay, we could use this end-stage cascade, so different CSTR reactors in series, and the more CSTRs we have in series, the more identical we come to a plug flow reactor. That's standard chemical reaction engineering. This has a yellow traffic light because the single-stage CSTR, the blue curve, is the one that delivers a really bad result. Now, the more vessels we add in the cascade, so here it's for 2, so this pointed blue line is the 2-stage cascade, we get a bit better, but you really would need like 4 or 5 CSTR in series as a cascade. So it's not worthwhile at the end of the day. So normally you would stick with a batch, repetitive batch, or plug flow reactor. Yeah, with this, we're at the end of this part of the biochemical reaction engineering. And I just want to cite at this, we can, a word said by John Cornford. He's a Nobel Prize winner in chemistry from 1975. And in his Nobel Prize lecture, he said, "It is no good offering an elegant, difficult, and expensive process to industrial chemists whose ideal is something to be carried out in a disused bathtub by a one-armed person, man, he said, who cannot read, the product being collected continuously through the drain hole in 100% purity and yield." Well, what does this mean? With your engineering background, you can think of the nicest, most complicated reactors to have the purest product. But at the end of the day, the most simple process is always the best, because you have the lowest chance of any damages, the lowest chance of any accidents, and it's the most safe process overall. And that always needs to be considered. Yeah, with this, we're at the end of the biochemical reaction engineering. And I'm just switching my sets of transparencies, because now we are going to start over. A moment, just switching files. Now we're going to start over with immobilization, what we're finalizing next time, and then continuing with case studies. Yeah, so the question is, why do we want to immobilize at all? Well, motivations to do so could be reduction of catalyst costs, could be enable continuous operation, could be easier process control to optimize yield and quality, but could also be even just using it in batch to have an easier product recovery by filtering off our catalyst easily as a heterogeneous carrier, and then just filter it off to recycle it or to spin it down and have cost reduction by recyclization of the bicatalyst or the product. And enzyme stability. It might, in often cases that we observed, increased enzyme stability if we heterogenize any biocatalyst. What we're going now to do in the following is I want to introduce you quickly one of the methods of immobilization. How could this be done? What are the standard methods? That's what we're doing today, and either we're starting off or we'll finalize this next week. We are going to talk about how can we, once again, from a biochemical reaction engineering point of view, characterize these immobilized biocatalysts for application. And at the end of this set of transparency, I will alternatively show you how ultrafiltration, membrane filtration works for homogeneously non-immobilized biocatalyst recyclization. Now, one point we have to consider is what is the maximum space yield we can reach per minimum reactor volume. So enzymes are normally optimized by nature for an aqueous environment. Has a low solubility in organic media, as you know. Therefore, an increase in the enzyme concentration is required to reach an acceptable space-time yield that makes it worthwhile to think in industry about application. And there are the term we're thinking about, space-time yield, is defined just for repetition, the mass of product divided for continuous process by the reaction volume V index R times the residence times that we have set for this continuously operated reactor, and space-time yield is expressed in grams per liter and hour, or kilograms per liter and day would be the unit. Now, one point that adds up to all those points that I mentioned before is that immobilization enables significant higher catalyst concentrations often in our reactor system. Why is it? Let's assume we solubilize an enzyme in aqueous phase. An enzyme is a protein, it's a macromolecule. And the solubility of this macromolecule until it starts to precipitate, or until it starts to be of the high, because of high concentration, to absorb as any surfaces in a fast manner, we're often limited. And therefore, a typical concentration of an enzyme that's being used is 5 grams per liter of native homogeneously solubilized enzyme in a stirred tank reactor. If we're immobilizing enzyme on support, typical values are 50 milligram of enzyme being immobilized on gram of a support carrier system. Meaning, now, since these particles we can pack in a plug flow reactor, generating a packed bed reactor out of this, so this crossed out lines here in the middle would be the bed of the packed bed of these in the middle, the enzymes that are immobilized. We could end up, if we are now calculating the enzyme load per liter of reaction volume, and the reaction volume is the liquid between the particles without the volume of the particles, because that's the volume, the liquid volume where our starting materials and our product being formed and transported. We would come up to 50 grams per liter and immobilized enzyme. So you see, we have a significant difference between homogenized, homogeneously soluble enzyme and immobilized enzyme. And this brings us also back to the reactor type discussion, where we said, remember, we have the batch, we have the plug flow reactor, we have the CSTR. The CSTR normally in a standard approach is operated as homogeneously soluble enzymes, but we can transform a plug flow reactor to the CSTR if we establish recirculation loop reactor, with recirculation flux being at least 20 times faster than the residence time flux. Yeah. And how do we term the maximum productivity in such a system? Now, we have one, the term of catalytic productivity, which in the end is nothing more than the turnover number, namely the mole of product you can produce per mole of enzyme. Enzyme deactivation can also be considered. We had defined so far the total turnover number in terms of all over batches, how much product we could define per enzyme being produced, but we can also express in a different manner that we say, okay, the TTN is nothing more than the expression of K cut divided by the deactivation constant. And both constants are dependent on temperature, the reaction rate of the system, and the deactivation is dependent on temperature. And therefore, this is also a view we can consider. And therefore, also decrease of temperature yields most of the time an increase of the TTN. However, space-time yield is decreased then because we can produce less because there's lower activity per time unit and volume. And this impact of the temperature might also be different if we have a homogeneously solubilized enzyme or if we have immobilized enzymes that we're going to apply. Now, what are the strategies for immobilization? Well, the strategies for immobilization that there are is we can either chemically bind in a covalent manner with a chemical bondage our enzyme, which is here the wall, to a surface. Sorry, shown here on the right side. Or we can have it in a non-covalent manner, so that we have any weak interactions, what we discussed also in the Biocatalysis enzyme technology lecture. So where we have a ion-ion dipole interaction, where we have a hydrophobic interaction. So at the end of the day, what we normally name adsorption. Watch out, we're differentiating ad, so to the surface, or ad with B, where it is consumed into the material. Here we're discussing about adsorption, attachment to surface. Then we still have, that sounds strange, carrier-free immobilization. There, the trick is that we have no carrier at all. We do have a high number of protein molecules, which we chemically bind to each other, and we get something like a big pile of wool. And because of now this high molecular mass we're generating by interlinking all the individual protein molecules, it's not soluble anymore, and it's solid in a liquid phase. So we have also suspension, and there we're differentiating two things: that's the CLAC, cross-linked enzyme crystals, from cross-linked enzyme clear aggregates. What is the difference? Well, the difference is that in the CLAC case on the left side, we work with to homogeneity purified enzymes, and in the right case, generating the clears, we're just working with impure enzymes, technical grade enzymes, where we know that there's no activity or foreign activity catalyzing a different reaction, our target reaction, but we do not have it purified to really homogeneity. Often purification is around 95%. Industrially, these were the CLACs were the first developed. Industrially, nowadays we apply the clear because the cost to produce these CLACs is much too high because of the high number of purification steps. Yeah, then we still have gel entrapment, so where we have just a gel, and in the gel we have integrated our enzymes. Here we have the challenge that for sure we always have to fight with diffusion limitation, because all our reagents need to diffuse into the material and out afterwards. So these three on top, carrier bound, carrier free, gel entrapment, that is the typical immobilization. That is what I, Andreas Liese, assign as immobilization. Now you have different lecture books out there in the world on biochemical reaction engineering, and depending who's the author, from what school they come, they often sometimes also address membrane retention. So if we have a membrane reactor, like an ultrafiltration membrane, and retaining homogeneously soluble enzymes, not attaching to the membrane, just in the volume, as heterogeneation, as immobilization. From my point of view, this is not true. So we are addressing, in my institute or the school where I'm coming from, we are addressing this as not as an immobilization method. Immobilization is always where we heterogenize something, adding it into some heterogeneous support or generating heterogeneous support. This goes all along up here with diffusion limitation. In the case of ultrafiltration, membrane filtration, the individual protein is individual homogeneously soluble, and therefore we do not observe any diffusion limitation. And therefore it's a three-dimensional reaction, in contrast to those up here, where it's always a two-dimensional reaction, because the substrate cannot access from everywhere our starting material, is limited by transport phenomena. Not true in the lower case by the membrane filtration. Therefore, in the following, I'm also excluding this here. Now I would like to discuss briefly what are the criteria for the selection of the immobilization matrix, where we want to bind, attach our enzymes to. Well, it should be having our reaction system that we want to apply. If it's an organic solvent, if it's an aqueous phase, whatever, a high mechanical, thermal, and chemical stability. If we would like to bind it to the surface here, like in the covalent case, We do need to have a chemical functionalization, or if we want to an adsorption, then we must have a clear hydrophobic or hydrophilic character. We need to have specific physical properties like density, mass, porosity. Mass makes a big difference. For example, if you have a packed bed, then we just like peppercorns, we stack the small individual balls into the column. But let's assume we have a fluidized bed reactor whereby having a flux upward and by gravity of the particle, we want to have them swimming in specific heights. Then mass and density is an important point. Then the stability of the immobilized catalyst, the resulting activity, and for sure, the cost of the resin, the base. Yeah, what are typical materials that are being used? These can be inorganic carriers like aluminum oxide, bentonite, porous glass, calcium phosphate gel, porous ceramic materials, or what we're also doing specifically in the last years here at the TOHH, close collaboration from our institute, for example, with Michael Schlüter, is that we use 3D printed, so additive manufactured materials where we bind to. Besides inorganic carrier materials, we can also use natural synthetic polymers. These are, for example, activated charcoal, polyacrylamide, carboxymethylcellulose, polyurethanes, oxyranes, agarose, alginate, dextranes, collagen, polyamide, or cellulose. So there's a vast variety of methods that can be applied. Now, in the next residual minutes, 5 minutes, I will start to show you the methods of immobilization, how we can bind these enzymes or enzymes to such surfaces. Let's start with gel entrapment. That is true for isolated enzymes or for cells. What is the idea? In the end, we have polysaccharides, hyaluronic acid, and or manuronic acid. How does this function? In the end, we have these polysaccharides, and the trick is that you see those have carboxylic acid functions. High number, so each carbohydrate, individual one out of the polysaccharide has a carboxylic acid function. Prior to the immobilization, those are connected with sodium ions. So it's sodium salt of this polysaccharide acid. Now, if we add calcium ions to this, the sodium ion is monovalent, just one positive charge. The calcium ion is so named bivalent, so it has two positive charges. And because it has two hands, two positive charges, it will bind two of these polysaccharide strings in contrast to sodium. Now, if at the time point where we add the calcium, we also have enzyme present solution, the enzyme will be trapped between these polysaccharide strings or the cells. And that is already the trick. How does this function in principle? Well, we have a solution made out of the polysaccharide, for example, and the cells or an enzyme. And then we have a bath. And in this bath, there's a calcium ion in aqueous bath. And now with pressure, we generate droplets that we let fall into this bath. And the droplet size that can be controlled by the pre-pressure and then the pressure that is cutting away these droplets coming out here determines the particle size, because this one is hardening in the calcium bath. As soon as it drops in here, the calcium will connect the two strings, and then we have our immobilization generated. To make this with higher speed, there are also different kinds of printers where we have a multitude, what you see here, a multitude of needles controlled with the same principle, pre-pressure over the stock solution, then pressure on the side to generate individual bubbles, and then we can print a multitude of particles at the same time. And down here, what the lady is holding is the calcium bath. That is one way. The other way is not entrapment, but we have a carrier material and DA cellulose, that's for example backbone cellulose, and we have here surface functional compounds which have a positive charge, and the enzyme in part because amino acids, so we have acids, negative charge, and we have just an ion interaction. You do not need for the examination know anything of these chemical structures here. We won't ask for this, but just the principles once again. Yeah, and the next will be the covalent mobilization methods. But to start up with this wouldn't make sense. We just have 3 minutes left. And I would quickly switch back to the Mentimeter and walk through the end. There I still have just 3 questions for you. Would be great if you rejoin there. So Mentimeter, code 207037116. And there you can judge, I hope it functions, I see no one, yeah, okay. There you can judge if you think that you understood the principles of bioreaction, that you understand the basic principles, or if you understood the basic principles of immunization. And the online lecture, how would you judge it? Do you see as a good alternative to the lecture in the auditorium? So I think because of the pandemic situation right now, it's from my point of view, it's a good alternative, but okay, I already see you see it rather mixed. For sure, we have more discussion going on. We're in the live lecture in the auditorium. Yeah, thank you for the feedback here. With this, we're at the end of today's lecture. I thank you for joining in. And yeah, looking forward to see you next week again. This lecture is being recorded. Therefore, by tomorrow, you will also have the video stream to take a look for learning afterwards, if you understand what's going on. Yeah, thank you very much for joining. Still wish you good week. Stay healthy. See you next week. Bye-bye.
Thank you, Prof.
Bye.
Recording stopped.